The first one, just looking at it, is that shift going to affect the domain? No. Is it going to affect the range? Is it? What is range? Range is up and down, right? I'm shifting left or right. Right? Because if I shift the x, I shift the x value. It's not going to affect the domain because the domain's all real numbers anyways. If I take all real numbers and shift them over 2 units, I still have all real numbers. So the graph of this, there's kind of 2 ways you can approach it. You know, one way you can approach it, you can say, okay, the general graph of the function of e to the x, or sorry, in this case, 3 to the x, would be 0, 1, and will look like that, right? And then I can shift that over 2 units. So this point is now 2, 1, and I have 3x minus 2. You don't really have to have the 3 to the x there. You can just know it's going to go through the point 2, 1. If I plug in,
like it's
you could say what happens when x is 2.
Yeah.
So g of 2 is 3 to the 2 minus 2, which would be 3 to the 0, which would be 1.
Oh, would be 1.
Yeah, remember?
Okay.
B to the 0 is 1.
Okay. What were the other ones? B to the 0 is 1, and then what's 3 to the 1 then?
3 to the 1 is 3.
So it would be.
So then if I plug in 3, then this point would be 3, 3. So domain is not going to be affected. It's all real numbers, minus infinity to infinity. This keeps going on forever, and this keeps getting larger forever. The range is not affected either from the original function. What is the range? 0 to infinity. Why is it not? Because, does that make sense why it's not 1? The horizontal asymptote starts out being the x-axis, and I didn't shift it up or down any. So my range stays the same.
You always want to start out, your range is always what you start out with, not what you finish with, right?
Your range is your y values.
Right.
And your domain is your x values. Your domain is what you're putting into the function.
Okay.
I can put any number in here with no problem.
Right.
But my range is what I get out. And you never get out a negative number.
Right.
You only ever get out positive numbers. And you can never even get out 0. And that's why you have an open parenthesis here. Which will be an important concept when we talk about 4.3 today, logarithmic functions. Because it's going to switch. We can never put in 0 or a negative number to a logarithmic function. You can't take log of 0 or log of -1. It doesn't exist. So we're switching the role of domain and range in that aspect. The next graph looks a little more complicated, but it's not. I can plug in a point. I can plug in x equals 2, just like we did above. If I plug in g of 2, I have 2/3 e to the 0 plus 2, which is 2/3 plus 2, which is 2.6, approximately. The shift the plus 2, that is going to affect my range, right? But my overall shape is not going to be affected. This point would be 2, 2.6.
But really, you could just go from 0, 1 right to up.
You could, but you would have to see how this 2/3 shrinks it vertically. So instead of 0, 1, it's actually 0, 2/3.
Oh.
Then I shift it to the left, sorry, to the right 2 units and up 2. So I have 2/3 plus 2, which would be 2.6, approximately. Right? All the other points are going to involve an E.
You plug in the 2 and you get a 0. Your X value is going to be at 2 and your Y value is at 2.
Your X value
Okay.
is
I
at
see, it's
2,
right there. Yeah.
and your Y value is at 2.6. Yeah, this is what you're plugging in. This is your X, and this is your Y. You only need 1 point. You could plug in 0 as well, and you would get some weird number, because you would have 2/3 times e to the minus 2 plus 2, which I can find the scientific calculator.
And the plus 2 is how you got your horizontal or vertical aspect. Is it vertical?
Horizontal.
Yeah.
Yeah. The plus 2, yeah. So that's going to affect my
You can't go below
domain or range.
your range.
Range, right? So the domain is not affected.
2.
You cannot affect the domain of an exponential function. It's always going to be minus infinity to infinity. But the range, in this case, is 2 to infinity. Because this plus 2 is shifting up the whole exponential function. So normally it was 0 to infinity, but now I shift all those points up and it's 2 to infinity. Fun stuff, right? It's a little disconnected because there's not a lot of connection to exponential functions, and there's even less to logarithmic, which is what we're going to talk about today. However, logarithms are just the inverse of the exponential function. They're tied together. They're inverses of each other. Like plus is inverse of minus, division is inverse of multiplication. Exponential and logarithmic are inverses of each other. They undo what the other one did, which comes really handy in solving equations, which is what we're going to do in the last section. So this one is, can you plug it in your calculator? Be very careful with your parentheses. If you're plugging this in your calculator, 340 divided by open parentheses, 1 plus 9 e to the caret, open parentheses, minus 0.31 times 8, close parentheses, or 0, depending on if you're doing the initial population. Here, the initial population is t is 0, which would be 340 over 1 plus 9 to the 1, which is 340 over 10. There's an e that might be your second function. It's usually by ln. Yeah, that's usually at second. You have to hit second and then this button. And then it'll give you as your exponent. So you don't need a caret on your calculator because it already puts you as your exponent. So if you plug in 0, you should get 34. Negative 0.31 times t. T is either 0 or 8.
Did you say you get 340? Which, yeah.
So that's good.
I didn't put that closed one on there.
You don't need to because your calculator already tells you it's up in the exponent. Some people's calculators won't show that.
So that's all I need to put in.
You should be able to hit enter. Make it 254. So now you can enter the same thing, come up here, and change the 0 to an 8. And that will give you your answer. So you can do the same thing too. Hit enter. You go up here. There. Change the 0 to an 8. So delete 8. And that's doing the exact same calculation, but with t equals 8. So I could ask you, what about t equals 10? The same thing. Then you plug in 10.
So, what, was it 193?
What did you
I
guys
think I
get?
did too many.
194.
194? I think, and yours has kind of a pretty print on it. You can kind
I
of
know,
see
I
up
don't know
there.
why I did all those. parentheses.
When in doubt, parentheses aren't going to hurt you, but they can mess you up. So what did we get? 194 or 193.87701825992? No, I don't know. But it says round to the nearest whole number. These came straight from Alex. So round to the nearest whole number in Alex. All right, you guys feel a little more comfortable with that? Sometimes these problems on the final, students are really intimidated by them because they think there's so much more to them because there's so much words, fish, butterflies, kitty cats. It doesn't matter what it is. It gives you the formula. Now in a biology class, they might give you the data and you have to come up with your own formula. But here, we're not doing that. Any questions on older material? We're going to make it through chapter 4, right? No blood is going to be spilled. Okay, 4.3 is logarithmic functions, which I said was the inverse of exponential functions. Your book likes to give you kind of this y and x relationship where an inverse function is if you have xy, the inverse is yx, right? The points. And that's what they're trying to kind of show you here. If I plug x into my log function and get out y, if I plug y into my exponential function, I get out x. Some students will try to memorize this and get really confused. I like to just kind of see what's going on in the problem and then do the inverse in each problem. And we'll do some examples of that. But some notes here. So we have bases with logarithmic functions, the same as we have with exponential functions. Both these cases are bases B. Generally, we'll have two types in your calculator, base 10 and base E. The base E is the natural log, and then we'll learn a change of base formula to calculate the other bases. But you can have any base. Square root of 7 can be your base. B is the base, and X is called the argument. So there's two ways you can write the same thing. There's logarithmic form and exponential form. A lot of people are more comfortable with the exponential form, but you can write the exact same thing in logarithmic form, and that's what our first couple examples are going to be. The converting, they try to show you this by replacing it. Some books teach you to memorize X and Y and then flip them. I like to just think log base 2 of 16 equals 4. Well, log base 2, the inverse with that would be 2 to a power, right? So if I can take 2 to this power and 2 to this power, inverses cancel my original thing. So if I have log base 2, the inverse is 2 to a power. So if I take 2 to this power equals 2 to this power, this would cancel the log base 2, right? 2 to log base 2 cancels because it's the inverse of each other. So I end up with 16 equals 2 to the 4th. You guys are probably comfortable with that, right? You guys have seen 2 to the 4th is 16. 2 times 2 times 2 times 2 is 16. But that is the exact same thing as saying log base 2 of 16 is 4. This is saying 2 to what power is 16? The answer there is 4. Here, it's an equation. It's already set up. That's like saying 10 over 2 is 5. That's what it's saying here. Log base 2 of 16 is 4. In exponential form, this is exponential form. What we're doing is we're transforming logarithmic equations to exponential equations. But the left-hand side equals the right-hand side. Do you guys agree 2 to the 4th equals 16? Do you agree that log base 2 of 16 is 4?
I do
I do now. The reason why is eventually they're going to get rid of this 4. They're going to not give you that. And they're going to say, what is log base 2 of 16? And you can say, well, what is 2 to the x of 16? 2 to what power gives you 16? 2 to the 4th. So my answer is 4. So I can write that in exponential form, or I can write that in logarithmic form. Let's look at the next one here.
Could you just look at it instead of doing the cancellation of log to?
You could in this one. Eventually, we're going to get into equations, and you're going to solve for an x value. So being able to cancel both sides is going to be very helpful. But yeah, at this point, you could look to say the exponential form here. This is what it's trying to kind of show you up here. If you have log base b of the x equals y, that's the same thing as y equals b to the x. So the base to the x power equals y. Here, y equals log base b of x. But I feel like students that try to memorize that get x and y and b confused a lot of the times. There's some videos out there that will actually kind of circle it and say this. They'll say the base to the exponential power equals 1 over 100. So this setup would be 10 to the minus 2 equals 1 over 100. I kind of prefer to say if I wanted to cancel the left-hand side, if I want to get rid of that log, I would take 10 to that power, since this base is 10. That's going to cancel this side, and I'm going to be left with 1 over 100. And I have to do the same thing to the right-hand side as I did the left-hand side. It's telling me the same thing. 10 to the minus 2 equals 1 over 100. Right? And the negative means I just bring it down to the bottom and square it, and 10 squared is 100. So this is saying the same thing as the logarithmic form. Do you guys see that? What was log base 7 of 1 equals 0? Yeah, 7 to the 0 equals 1. So if I take 7 to this side and 7 to this side, it would say 1 equals 7 to the 0.
So,
Log base b of 1 is always going to be 0.
on B,
Mm-hmm.
how you did on A, you did the 2 and then the exponent
Mm-hmm.
equals 16. Could you do that with B?
Yeah, this is
To the
saying
X?
10 to the x is 1 over 100.
Oh.
Eventually, we're going to not have equals. We're going to have to solve for it. Right now, we're just translating an equation that has a left-hand side and a right-hand side, and we're exchanging it from the logarithmic form to the exponential form because they're together. They are pairs. The next examples, we're going to change exponential to logarithmic. So we have an equation. We have a left-hand side equals a right-hand side. Eventually, we're going to only have a left-hand side, and it will equal. We have to solve for what it equals. 3 to the 4th is 81. What is that in logarithmic form?
Log base 3,
Mm-hmm.
81.
Very good. You guys see that? So an easy way to do it is I could take log base 3 of this side and log base 3 of this side. Log base 3 of 3. So I'm left with 4 on this side, and then I have log base 3 of 81 on the right-hand side. I kind of prefer this method because it makes solving equations easier later on, but you could have seen from A that is log base 3 of 81 equals 4. Log of base 3 of this side, log base 3 of this side, that's going to cancel. 4 equals log base 3 of 81. You guys see that? It doesn't matter which order you write it. This is the same thing as this. So what's B?
Log base 10.
Mm-hmm.
1 million equals 6.
Good.
Whose opponents?
So that's saying log base 10 of a million is 6. And that looks like a B.
10 is usually the assumed base.
It is. So on your calculator, yeah, eventually we'll get there. It's understood log, if it's not listed, it's understood it's 10. What about on C?
Log base,
Mm-hmm.
log bed
Good.
of 5
Mm-hmm.
equals -1.
Good. So if I take log of 1/5 of both sides, I have -1 equals log of 1/5 equals 5. Right. I take log 1/5 of this side and log base 1/5 of this side. I end up with -1 equals log base 1/5 of 5. Do you guys see that? So just to kind of, give you an outline, if they want you to write it in exponential form, that's going to be b to y equals x. If I want to translate that or transform it to logarithmic form, I have y equals log base b of x. So this is saying b to the y equals x. So some, methods kind of teach that, but to get rid of log base b, you take b to that power on both sides. To get rid of b to a power, you take log base b of both sides. And you can always cancel it out and end up with whatever form you want it in. So let's look at the next examples. Evaluate the expressions. You cannot plug these in your calculator.
Why?
Because your calculator is only base 10 or base E. We'll eventually get to the change of base formula, which you can plug it in your calculator, but right here you should be able to calculate it in your head.
So,
One of them does work.
One of them works, the one.
Well, 2 of them do, just not the half. I think. I don't know.
It works.
Depends on how you're plugging in your calculator.
Well, I mean, mine set up where you just have log and then.
It gives you a base?
Yeah.
Okay.
Yeah,
So-
ours doesn't.
Yeah, most of them don't. Question? Gonna answer it? Okay, so let's go through this one. The easiest approach, I think, and it's the reason why I think it's easiest because it makes your life easier later on, is to say, okay, what am I trying to solve here? Let's call it y. I don't know what it is, but I want to solve for y. What can I do to the left-hand side to get rid of log of 2? I mean log of 4. Yeah, I can take 4 to that power, right? 4 to the 4. That gives me 16 equals 4 to the y. So what power y gives me 4 to that power is 16? So this is y equals 2. You see that? So if I just look at here, I can see this is asking me 4 to what power gives me 16. 4 squared gives me 16. Yeah, so here, 2 to what power gives me 8? 3. So if you don't know the y, say, let's call it y, I take 2 to this power, 2 to this power, this gives me 8 equals 2 to the y. And then here, y would be 3.
You have to write it as y.
You don't have to, because this is just equals, this would just be equals 3. The reason why it comes up, because in 4(3), you're going to have expressions like this. And eventually you're going to have, I don't have them on here. Spring, F-130, notes, 4, 5. Eventually, we're going to have equations. We're going to have stuff like this. So I might want to take log base 3 of both sides and solve, because eventually that's where we're going to get into is find the variable x. But here, you're only solving one step. So it doesn't really make sense to call it y, but if you do, it makes it a little easier later on. Baby steps. Where were baby steps here? So what is C asking? This is saying 8 equals 1/2 to some power. Not 16. -3. 1/2, since it's
Oh.
does that make sense?
I was-
You were multiplying
I
2
was
times,
multiplying.
yeah.
Sorry.
So this would be y equals -3. And that's another reason why it might be beneficial to write it this way. So you can say, oh, I have a half. I need to get to 8, so I know it's going to be negative. And then 2, 4, 8. So my power's 3, but it's negative since it's a half to start with.
For me, I rather than a y, even though that.
You use x.
I use an x and I just put that in the little this and then I split up 1 and 16 for the next like 4 to 5 hours. So it's basically the same thing. Just,
Yeah, you just say 4 to the x
Yeah.
equals 16.
so I just-
Yeah. This book uses y for the logs.
Yeah, I got that.
Yeah, so that's why I just try to be consistent with it. B to the x equals y. So this is saying b to what? This is saying 4 to what power is 16.
Yeah.
2 to what power is 8. A half to what power is 8. And then I get my answers there.
Yeah, technically, like the x is 16. If you want to go with it.
Yes, the form that the book gives. So the common definition of logarithmic functions in your calculator is base 10. If you have a calculator that only has base 10, you have to do change of base formula, and we're going to get to that later on in chapter, I think, 4.4. So when we actually do solve for that x, we can plug in log base 3 of a number. Yours does it pretty simple with a thing, with one step. Most calculators don't. So if they drop the base, it's understood it's base 10. Right? Like they have here. If they give you this, y equals log of s, it's understood that it's base 10. There is a special logarithmic function that's called the natural logarithmic function that comes up a lot. And it comes up a lot mostly in calculus because you don't have to worry about the coefficient when you do change a base. So it can be written 2 ways. It can be written log base e of x, but generally it's just written as ln of x. Your calculator probably has 2 buttons on it. It has a log button and an ln button. Ln of x is the inverse of e to the x. Log of x is the inverse of 10 to a power. Evaluating common logarithmic and log and natural log functions. Log base 10 of 100,000 is what? 5. This is saying 10 to what power is 100,000? So this is base 10. 10 to what power is 100,000? That would be 5. Here, this is saying 10 to what power is 0.001? -3. This is saying 10 to the x is 0.001, so x is -3. ln of e to the 4. What did I say about ln and e? They're inverses of each other. They cancel each other out.
Okay.
So ln of e would just be 4. ln e to the
ln
fourth.
E to the fourth.
Yeah.
And then hit equal.
Yeah. What about ln of 1 over e? Close. -1. So another way I could write this is ln of e to the -1, agree? So the ln and e cancel each other out, and we're left with -1. So you can plug these in your calculator, or you can just know. Eventually, they're going to be more complicated. We're going to get to equations and solve for the values of x that make them true.
Is that where the calculator will come in?
The calculator will come in because we're solving for a value of x. We'll have to take the ln of both sides or the log of both sides, and it won't really matter the base, but we'll do it to simplify it. Here's some examples of using your calculator. What is log of 5,809? This is 3.764101. If I approximate it to 4 decimals, I get 3.7641. Which makes sense because log base 10, you know it has to be over 3 because 10 to the 3rd power would be 1,000. But it's between 3 and 4, right? Because we have it 10,000, 1,000 and 10,000. And we'll get to more of what makes sense there later on, but right now it's just plugging in your calculator. Did everyone find their log button?
Yeah.
I don't know. There's a log button, but like.
So this is log and this is LN. So you hit log and then type 5,809.
And then if you close it out,
Yeah.
5,809.
Oh.
5,809.
Okay.
And then hit enter. You can close the parentheses and hit enter or just hit enter.
Oh.
So that gives you your number. Which should make sense in some cases because we know the base is 10, so it's between 1,000 and 10,000. So it's going to be between 3 and 4. If it's a decimal, then the exponent would be negative, yeah. What about ln of 472? 6.156978. This one's a little annoying rounding 4 decimals because if you round 4 decimals, you have to round actually to 70. Anyone not getting that? Okay, so you have this log button. Log of the first one, you just plug in 5,809. Then you can hit enter. You'll do that. The next one you're looking at ln. So you have the ln right below it. And then you plug in 472. Some of these could be in scientific notation. Just looking at this one, what would you assume the numbers to be between? Kind of gives you an idea here. 10 to the 7th. So the number's going to be between 7 and 8. So this would be 4.6 times 10 to the 7th, which would be, if I move the decimal 7 places, I would get 1, 2, 3, 4, 5, 6. So that's 4,600,000. You can put it in scientific notation in your calculator, or you can expand it out. So if I take the log of this, I get 7.6678, which makes
I got 7.6627.
27. Oh, that is what I got too.
I got
27.
round up.
Rounding up.
8, 27 or 28? 28.
Rounding.
Yeah. Because it would be 6627578. Did you put, you probably lost a 0. Yeah, you lost a 0. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. I did 4. Yeah, I got an extra. Yeah. Duh, you grouped the second group in 4s, not 3s. You didn't know that rule? Hello? No. But there is some way to kind of, visually get this idea of what the number should be between. Eventually, we're going to use this to solve for an x value. What's ln of 0.05? We would expect it to be negative, right?
Negative 2.9957, but not rounded. But it's just
Because the next number is a 3. So it is rounded. Or just cut off. It's called truncated. In computer science and stuff, they say you can either round it or truncate it. Truncate it is when you just cut it off.
I remember like in elementary when it would proceed like that, you'd have to put a little
Remainder bar.
yeah.
If it continued the same.
Yeah. Do we even still use
No.
that? Okay, so
And that would only be in the case of like 1/3.
It's repeating.
It's 0.333. Yeah, repeating. You could write that 0.3 repeating.
Right, so why don't we use that still?
We could if we wanted exact value, but a lot of times we just need an approximation. So 0.33 is fine, or 0.3. Yeah. 0.666 might be 0.67. Yeah, it doesn't really matter. Okay, properties of logs. People like to memorize these, but I never like to rely on my memorization power, so I like to think about it. If I have log base b of 1 equals 0, that's saying b to the 0 is 1, right? I could take b to this power and b to this power and get b to the 0 is 1, right? The same thing, log base b of b, that's 1, because if I take b to this power and b to this power, b to the first power is b. B to the first power is b is the same thing as saying log base b of b. So some of you like the idea maybe of just memorizing this, because sometimes I, write, to get rid of log base b, I take b to that power. So whatever I do the left-hand side, I have to do the right-hand side. This cancels that out, and I'm left with b equals b to the 1. This is kind of saying the same thing here. Log base b of b to the x, that's going to cancel out, and I'm going to be left with x. X equals x. The reason why x equals x is because b to the x equals b to the x. Saying b to the x power equals b to the x. X equals x. This is the whole reason why we can cross out log base b times b to a power. And number 4 is saying the same thing. B to log base b of x equals x. Log base b of x equals log base b of x. Here's some examples that come in handy. And that we've already kind of been doing this. You can see this? Log base 2 of 2 is going to cancel out, it's going to equal x. 2 to the x equals 2 to the x. So agreed that most of your calculators can do this, or some of your calculators can do this, but let's actually go through and calculate these. Log base 3 of 3 to the 10. Log base 3 of 3 cancels out, and I'm left with 10. ln of e squared. 2. What is log base 11 of 11? 1. What is log base 10 of 10? 1. What is log square root of 7? Log base square root of 7 of 1? It is 0, because square root of 7 to the 0 power is 1. Anything Log or ln of any base to the first power is always going to be 0. That base to the 0 power is always going to be 1, right? So this is saying square root of 7 to what power is 1? 0, right? Because if I want to label this as x, I take the square root of 7 on this side, square root of 7 on this side. I have square root of 7 to the x power is 1. That only happens when x is 0, right? What about ln of 1? 0. Ln or log of any base of 1 is always 0 because that base to the 0 power is 1. What about g? What is the 5 in log base 5 doing?
Well, it's 5.
It's canceling out. What am I left with? C squared plus 4. Eventually, you're going to have to come up with what to do to cancel out the log base 5. And you're going to raise both sides to the 5th power. What about 10 to the log of a squared plus b squared? A squared plus b squared. So these two are really kind of foreshadowing 4.5 when you have to solve for a or solve for c. Eventually, that's what we're going to get to, these equations. So let's look at real quick, the last 5 minutes, graphing logarithmic functions. Again, it's going to be like graphing exponential functions. There's really going to be one interesting point. And it's either going to increase or decrease. The domain and range are going to be switched from the exponential function, right? Here's exponential functions. Let me highlight. This one is the inverse of the yellow one. When I take the inverse, I reflected about the line y equals x. That's switching the role of x and y. So in this case, my domain for my exponential functions was all real numbers, meaning my range for my logarithmic functions all real numbers. So my y values are going to be all real numbers. And it's going to either decrease or it's going to increase. It's the only interesting part. The range in the exponential was only positive numbers. That means I can only input positive numbers to the logarithmic function, meaning my domain is only from 0 to infinity. So in the logarithmic function, a shift left or right will affect the domain, but nothing's going to affect the range. Versus the exponential function, you couldn't affect the domain, but only shifts ups and downs could affect the range. If b is greater than 1, it's increasing. If it's from 0 to 1, it's decreasing, just like it was with exponential function. So you either start up here at the top and go down, or start at the bottom and go up. All the points will go through this point 0, 1, because in the exponential function they went through 0. I said that backwards. All the points will go through 1, 0, because in the exponential function they went through 0, 1. And I'm reflecting it about the line y equals x. So I'm switching the role of x and y. So you can see here, I have an example of when b is greater than 1. And then here I have an example when b is less than 1. They will go through the same point though, this 1, 0. So we'll start with graphing some logarithmic functions, looking at the basic function and shifting it to the left or right. We have so that's what we'll end up doing is when the input is positive. I'll see you guys on Wednesday. And the sign-in sheet go around. Anyone else have a quiz 6 to turn in? They can turn that in.